Okay, so we've now gotten a very brief introduction to sequences. We've formally defined a limit, and just in case a limit actually doesn't exist, we should formally define that as well. So for example, let's take the sequence of natural numbers, 1, 2, 3, 4, etc. That clearly does not converge to a specific number. So we're just going to define that, and we'll say if limit as n approaches infinity of a sub n is equal to infinity. I'm sorry, not if. This is true if the following. If for all positive integer m, there exists a positive integer n such that if n is greater than n, then a sub n is greater than m. That probably, again, looks a little bit strange to you upon first investigation here. What that means is, no matter what value I pick, m is going to turn out to be like your proposed maximum value. If it converges to some value that's very large, let's say it converges to 1,000,000, then let's propose that as our highest value that this converges to. This n is going to function just like the n did in our previous definition of a limit. So what we're saying is, if you can pick a value, n, and you make anything bigger than it, then this time, rather than getting really close, rather than having like a sub n minus l absolute value is less than epsilon, now we're going to say, if you pick a sufficiently large n, so you go sufficiently far into your sequence, then it will always be bigger than whatever value you just proposed. So let's say we're playing, basically the game is like, okay, I think the biggest your sequence will ever get is 1,000,000. Let's use million for m. If it's 1,000,000, then if the limit is this, if the limit is infinite, the onus is on me to show you that I can produce a term number sufficiently large to exceed 1,000,000. So I might say, oh, well actually, hold on a second, if you go to the 73rd term, a sub 73, it actually turns out to be bigger than 1,000,000. Now, I'd have to be a little bit more rigorous in establishing that rather than just stating the fact. But that's the basic game that's played. Okay. The way I always think of this is, you can always make it bigger. So if somebody names a value, no, I can always name a value that's bigger than yours. Or you can't impose a ceiling on the sequence. So if the proposed ceiling is m, well, I can produce something that breaks through that ceiling. Okay, so let's consider now a few sequences and series sequences for now. And they do not necessarily have to do with this. And actually, rather than formally finding the limit and proving the limit, our goal from here on out really is going to be just analyzing these things and finding the limit of the sequence, whether or not it converges, rather than proving them formally. So think about when n goes to infinity, what happens to that. Maybe hit pause. And hopefully you decided that this is equal to 1. It'll be 1,000,000 over 1,000,001, or 1,000,000,000 over 1,000,000,001, which is very close to 1. You can see what drives the behavior is that n, and that 1 has very little to do with what's going on here. So one technique here is that you can divide through by the largest power of n. So n divided by n is 1, n divided by n is 1, plus 1 over n. And now I think it's very clear to everybody that as n gets large, this little thing goes to 0, so we'd have 1 over 1, which is 1. Okay, we won't be needing for that. Okay, another sequence, taking the limit as n approaches infinity of the natural log of n over n. I'm not putting in an absolute value here because n is going to be positive. If you put a very large number in here, just mentally put a very large number in here. Natural log of a large number is a large number. Well, putting a large number in for n, you get a large number. This thing's an indeterminate form, so we don't really know what's going on here, which infinite is bigger, that sort of thing. But we do have L'Hopital's rule. L'Hopital's rule says that if you have a function over a function, and when you take the limit of that thing, as n approaches infinity, you get indeterminate form, which is infinite over infinite. If both functions are differentiable, then this is actually the same as taking the limit, as n approaches infinity, of the derivative of both. Notice that when taking the derivative of these, we do not apply quotient rule or something like that. We just take the derivative of the top thing, take the derivative of the bottom thing, and L'Hopital, our French friend, tells us that that limit of the derivatives is actually equal to the original limit itself. So if we apply that rule here, we'll get the limit as n approaches infinity of, take the derivative of natural log of n, take the derivative of n, we get 1 over n over 1, and now the limit here will be 0. Which tells me that, looking back at my indeterminate form, it turns out that this guy was getting bigger faster than that one, right? Because if the numerator was getting bigger quicker than the denominator, then we would have had a larger numerator and a smaller denominator. But you can't tell that just by looking at it. So L'Hopital's rule can be a useful way of analyzing the convergence of sequences, or limits of sequences. So now, what this one's saying is basically, think about this as just like an intellectual exploration of which is bigger, faster. Is n factorial bigger, faster as you get larger and larger n's, or is n to the n bigger? Okay. This may not, maybe you have a guess. I think if you just thought about these two, you could probably decide which one is bigger, faster. But, so, we're going to show that this thing turns out to go to 0, and that's because this is equal to the limit as n approaches infinity of 1 times 2 times 3 times n over n times n times n times n. Now we can take this and factor out 1 over n. We're really not factoring out, we're just sort of segregating it from the rest. Okay, now the stuff in parentheses, all of this is guaranteed to be less than or equal to 1. And if you're wondering, like, how could it be equal to? Well, if n is small enough, it could be. So if that's less than or equal to 1, then this whole thing, that whole line, is less than or equal to that. Right? Because if that is smaller than 1 or equal to 1, then 1 over n times this will give you something that is less than or equal to just the first term 1 over n. And now I know that that's actually, this limit goes to 0. So that limit must also go to 0. I should say also that just to, if you might have just had a solid nuanced thought, which I did, that I didn't really show. I showed that it's less than something that goes to 0, so how maybe it goes to a negative number. But I could also right here say that 0 is going to be less than this whole thing because n is positive here. So now my sequence is sandwiched between 0 and 0, and of course, so we could use the sandwich theorem to say that this whole limit then is equal to 0. Okay, and one more quick one. Okay, so there's the question. Now I've posed it in terms of a variable r raised to the nth power. So as n goes to infinity, of course, you'll get r to some really big number. The question is, does this ever have a limit? Does it converge to anything? Or does it just diverge no matter what? So think about it for a second. And hopefully you're now at a point where you've thought and you're playing it again. This actually, the way this guy's going to work is that limit will go to 0 if get rid of this stuff. It'll go to 0 if r is between -1 and 1, or you could say absolute value of r is less than 1. And if you're wondering why, if you picture like a half raised to a very large number, well, that gets very, very small, so it goes closer to 0. This will be equal to 1 if r is equal to 1, right? Because 1 to the 5th, 1 to the 6th, 1 to the 7th, it's 1 every time. And then otherwise, it's going to diverge. And this, basically, you're looking at a geometric sequence here, so hopefully that makes sense. What we're going to do in the future in this unit is push ourselves further in with respect to finding limits not only of sequences, but finding limits, if they exist, of series. When remember, series is just the sum of a sequence. So right now we've just really scratched the surface on techniques for finding limits. You can take entire courses on this at the undergraduate level as well. So real analysis deals with a lot of these kinds of things. Okay, that's that.